Today I will be discussing the most critical framework, that is skyline of the urban India, the Indian code of high-rise building. As our cities grows vertically, our city grows vertically, understanding the guideline that ensure that structural safety, functionality, and the compliances become an essential for every structural engineer, architects, and the builders. In the next few minutes, we will explore not just what code says, but why it says it, and how we can apply it more intelligently in the real world. My forte is I have designed almost 200-meter buildings in the NCR. Almost 5-6 buildings is designed in NCR, that we have designed 4 or 5 buildings in that. Now we are discussing the structure. This is our point we will discussing in our presentation. When we start the design, we can follow the what have been designed so far. In the high-rise building, this is in the world 1900. Already started in Philadelphia, about 167 meter. In the last 5 to 7 years, we have started the design more than 100 meter in the India, except Mumbai. This is a composite design. We can see the almost 90% of the beam, 90% of the buildings are composite. Composite is a group of interconnecting elements that collaborate at the runtime to achieve the superior properties. The combining of the steel and the concrete develop the composite building system. Basically, the composite structure is steel frame stabilized by the RCC. The high strength concrete gives you economy, damping characteristics of the large element combined with the lightness and compactability of the steel frame. Composite column is almost 4 to 6 times cheaper than the steel, and the 40 to 100% composite beam cheaper than the steel beams. Without the composite structure, many of our tall structure may never built in their form. Design philosophy of the composite building: first, we had the gravity system design, second lateral, third one is the connection design. Codes is available in the market: IS 1600, 1700 and IS 1134. This is the IS 384 comes last year, but before that we are following AISC or Eurocode 4. In the gravity design, suppose there is the 11 by 11 meter grade, there is a 2 combination, option 1 and the option 2. The option 2 is generally follow the in the market. But we have developed, this is the first time in the world, we have crisscross section. This is used in the Embassy Tech Village Parcel 5 in Bangalore. That was the 35 lakhs square feet of the building. Therefore, this crisscross systems gives you a primary beam and the secondary beam is the same depth. If using the option 2, when all the secondary beam resting on the primary beam depth will increase. Now we can start the lateral resisting systems. First and the second, we will discuss the design of composite beam, deck, and the column as per the latest code. The lateral resisting system, this is gives in the city visual some paper. There is a type 1, type 2, type 3, and the type 4 systems are given in. This is taking in the tubular. First is shear frame, second interactive system, third is partially tubular system, third is the tubular systems. When we are comparing with our Indian standard IS 1600, it is giving this, our IS 1600 is generally designed for the RCC structure, not for the composite or steel structure. Because when we are comparing the RCC versus steel or composite, the stiffness, lateral stiffness or the vertical stiffness is very, very less compared to the RCC structure. The code should be different, but it is not available in our IS, or we can refer the IS 16700 or any international code. Even RCC, this is the design, this 16700 gives the more than 50 meter to 250 meter buildings. But in this particular, this table number 1, it's in the zone 4, you can design up to a 180 meter. It is a not, I am not agree with the code, because this is a 250 meter high building. When we are designing in the zone 5, it should be there. Generally, when you are designing the tall structure, the governing lateral force is wind, not earthquake. Where we are designing higher and higher, our wind force is governing, and the stiffness is very less. Therefore, the earthquake forces also is less. So therefore, all the high-rise building is designed with the wind system. This is a flared. Flared means you can give the higher width or depth at the bottom and lower at the top, so that our wind force is going like the cantilever action. Second is the bundle. The bundle means small pieces, tube and tube, include 4, 5 together, and we can stop at every 4, 5 whenever you want, as per your design. This is the mega frame. Mega frame is you can apply the more jumbo column and the super column in your structure. The stability of the jumbo column and the mega column is much higher than this distributed small columns. We can discuss in the later. Third one is the link. When 2 towers combined with that, it gives you more resistance in wind. It will also, we can discuss in the later. Third one is a tripod. This is one leg of the tripod is go above, and the second and third rest is terminated at the lower floors. In the lateral resisting system, one of the most critical things, the aspect ratio. The aspect ratio, when the aspect ratio is less than 6, it is easily, you can design easily. The preferred section. If this aspect ratio is more than 6 and less than 10, you can manage with what kind of the system we have presented in the CTUB or you are in ISS passing. When the aspect ratio is more than 10, in that case you require the spatial system to resist the lateral loads. That building we are showing in the plan, this width of the building is only 10 meter and the height of the building is 140 meter. I have never designed. This is only 140 meter, but this is the more complex than the 200 meter height buildings, because its behavior of the building almost skyscrapers. The spatial provision is like this in the conventional design philosophy is to increase the strength to resist the lateral forces. Like you can increase the shear wall, you can provide the braces. This is a conventional philosophy. But structure control is the modern philosophy to controlling the undesired response under the earthquake and wind. So there is the 2-3 option is available. This is the one is the tune mass damper. This is the tune mass damper placed on the top of the high rise to control the wind or drift. Second one is the friction damper. Friction damper, we have introduced the friction damper in the first time in India. And we have installed almost 12,000 to 15,000 friction damper for the Unitech in the zone 4 and the zone 5 building. The disadvantage of the friction damper is it is used only in the earthquake region, not a wind. Because earthquake is the inertia force and it provides the extra damping, additional damping to the structure. And the wind case, I have designed the one building in the Gurgaon. This is a G+6 and I am converted into G+12. And because this is the existing building and the width of the building is very less, so we are not able to provide the shear wall. In that case, we have strengthened the column with the gravity load and provide the viscous damper to resist the lateral load of wind as well as earthquake. Because this length of the building is very high and the width of very less, so this building is also governing in the wind. So we don't have no another option than the viscous damper. In the lateral load system, if you will check, if this is a 10-story building, the load, if 20-story building, the load will become a double and movement become a 4 times and deflection is 16 times. When you go slowly higher, this is the deflection will be a critical, not a movement and the load. And This slenderness, maximum slenderness is also given in our IS 1600. I don't know why they are giving. Because in our code they are saying you can control the drift, you can control the deflection, you can design with minimum base shear as they are giving. So I don't know why they are giving the aspect ratio for this. I think it is a more critical. This is a medical. It is a more critical is the you can register, you can design the building for the everything drift, deflection, and the base shears, not numbers. The overall limit under the wind load is HY 500 and the internationally HY 500 to 400. In India, HY 500. The inter-story drift under the wind. In India, this is again HY 500, and the international HY 800 to 350, depending upon the country to country. And the seismic in the India HY 250, and the international, it is depending upon HY 100 to HY 50. All the serviceability criteria like a deflection and this is the human comfort criteria, not a design criteria. And when your deflection goes up, so this is your secondary member, the non-permanent member will crack. So therefore, they are limiting this. And after the certain limit, the human is feeling uneasy under the larger deflection. That's why the human comfort criteria coming into a picture. This acceleration given in this 16700, it is I think for the RCC structure and for the 20-year wind. And the internationally, we are giving internationally even US in the American code. This is this is almost same. Residential and the mercantile 0.18 and 0.25. In the residential internationally 10 to 15. This is almost same. When we are designing the high rise, first of all we decide what kind of the plan is there, and plan is there. Then you can provide which plan gives you more resistance to the lateral loads. One rectangular, circular, and the triangular. You can see in the option 1, we are placing the more jumbo column at the corners. It gives you a better stability compared to option 2. Okay, the circular and the polygonal. The second option, when the rectangular width is 1, the polygonal and the circular width is 1.1. with the same area concept. And again, we are discussing with jumbo column and the small distributed column. And third one is the triangular. Triangle is the width of the triangle is the 1.5 times against the rectangular column. In that case, you can see there is a 3 type of the building. In the triangular, the inertia of the lateral inertia of the building is 0.7 to 1.54. Width is 1.52. In the rectangular, 0.67 to 1. Width is 1. And the polygonal or circular, this is 0.64 to 0.71. And width is 1.13. This is the plans. If you can plan the building and you can plan the high-rise building, so you can consider the plan of consider the lump corner is stiffness of the lump corner is better than distributed small columns. Now aerodynamic shape factors. This is the given in our IS 875 part 2015. The drag coefficient in the square building is more compared to circular and polynomial and triangular. Vortex shedding. The part of the vortex shedding begins when you goes higher and higher. The wind is critical. Then the vortex shedding is coming to a picture. This size of the vortex depends upon the shape of the building. If the circular, then the crosswind moment is very high. Then coming to a triangular, rectangular, and the last one is if you are providing some opening in the structures, that it's reduce the vortex shedding, and your across the wind deflection is coming less. The shape also reduce the wind vortex shedding. If you provide some stairs all around the building, it reduces your vortex shedding effect. And openings also we have altered. And the third one is the rotate and the twist. This one. when you are designing the building with the opening and you can reduce the sail area. Okay. In the lower portion, you can design the building length is very high, and at the top you can twist. Then the force at the upper level is less and the lower level is higher. Like this. This is a practical example of the building design with the wind forces. In the bottom, there the length is higher and the top width is higher. Seismic design, this is this is as per the IS 1893, and the I think time period is given in the IS 1700. It is now the time period is not directly proportionate to the stiffness. This is directly proportionate to the height. Foundation design. In the foundation design, you require the rigorous soil investigation, and this is when you go high, this is settlement is the big issue under the high-rise building. This is the high related. When you are designing the building higher and higher, there is a shrinkage and some settlements coming in the columns also, like a beam. When you are designing the steel beam and it's the construction state, there is some camber is coming, and some deflection is coming, and we are providing the camber in the beam to compensate the deflection. Same here. When you are designing the high-rise building, you can provide some sensor in the building and what kind of the shortening in the column. So you can adjust this shortening at some floor, some after floor, maybe a 20, 30, 40, 50 floors. Because the load of the column is very high, and due to concrete, this is coming the creep shrinkage and the shortening is coming there. And the sequence of the construction is also more important in the high-rise buildings. And the verticality during after the construction. This verticality is automatic come when you are going with the steel or the composite design. It is not happen in the RCC. This is happen in the RCC structure. You can maintain the verticality also because it goes beyond the permissible limit. It gives you extra forces in the building. Now we are discussing about the composite beam. Okay, as per the IS 11384, the first part, it is giving the load combination in our IS 11384. Generally, we are designing the building or buildings. So we are refer the code IS 875 part 5. But now this combinations gives in the IS 138. It is the more or less similar with the IRC 6 code, with the leading and the accompanying and the variable depending upon. Second is the partially factor of safety. This is especially I am mentioning this because when we are designing the composite or steel structure as per the Euro code or AISC code, this partial factory factor for the materials, particularly for the steel, this is the 1. But in our code, it is given 1.1. But nowadays we are exporting the lot of steel to the another one. They are using partial fracture safety is 1 and we are using 1.1. Therefore, if we are using 1.1, the structure steel consumption is increased by the 10%. So I am requesting to quote, you can do 1 only because nowadays the manufacturers gives you very good quality of the steel. That's why we can go for the 1 only. And the second is concrete as well. As per the stress block, as per the Indian code, stress block permissible value of the stress is 0.36 FCK. When you are using the Euro code 4, it gives you 0.45 FCK. This is also again 1.5 times higher than our Indian code. This classification is given in the 11389, and one important clause given as clause is also given in the IRC and the Euro code 4 as well. This is when your web is slender, then you can avoid this 4 number of the area neglected, and you can treat this section as a class 2 only. Second one, when we are designing this composite beam, the most important is the effective width of the beam, effective width of the composite beam. And this effective width given in the our IS 3384, it is the almost similar to ES4. This is the, I think, copied from that there only. In this case, the effective spans is also given in the our code. This is the first left hand. This is a 0.85. Second is 0.7. Third is the cantilever. This is a double the cantilever. And the width given is B0 plus L by 8. And ACI, it is directly given the L by 8 of the both side. In this our, I don't know why they are B0 what. Why we are considering the B0, which is a very lesser thickness. And this is the effective width when we are designing the sagging moment is the separate, different, and when we are designing the hogging moment, it is the different. Hogging moment, the effective width of the slab is slightly lesser than considered to the sagging moment. And we are considering, when we are designing for the hogging moment, we are codes assume the laterally restrain the I section, not consider the effect of the slab. Only neglect, we neglect the concrete area. But resistance is also provided. That's why the capacity of the beam comes in the hogging moment 100% plastic moment capacity. This is the design of the member, steel member. When we are talking about the composite construction, always we have designed in the two stages. One is construction stage, second is the composite of the final stage. Because when you are designing the beam, deck sheet or column, in the column as well, when you are putting the concrete load over there, so it's behave as a steel only. So you are design in the construction stage steel section only, not you can take the advantage of the concrete. In the first, we are designing the plastic moment resistance of the section as per this, and I already told, because the gamma zero is the 1.1, so you are reducing the plastic moment capacity is the 10% lesser compared to the international code. And second, we have already discussed this lateral torsion buckling resistance. This is exactly as per the IS code. And the length you should consider 0.25 of the L1. This is for the hogging moment. This is for the hogging moments. Third stage is the hogging moment design. In the hogging moment design, this is the slab is already restrained your beam. So first, what is the capacity, moment capacity of the plastic moment capacity is the steel. This gives you a first case. And the second, we are ignoring the concrete, and what the capacity, this is the reinforcement coming under the effective width, you can consider it gives you a higher value of this beam capacity. It is already mentioned, this is a 1, 2, 3, 4, 5th, 6th line, MPRS. This is the MPRS is the capacity of the reinforcement. And 6th one, the moment capacity of the section and moment capacity of the erection is total capacity. And the last one, in the hogging moment, when the plastic moment capacity of the shear is greater than 0.6 times of design value of shear, in that case, the reduction factor of the bending resistance coming into a picture. This is beta multiplied by the MP. The beta value is given in the IS 1187, and it is similar to the again Eurocode 4, because our code is totally similar to the ES4. And this hogging moment capacity gives in the appendix IS 11. This formula is given in the IS 11384. And this shear value is slightly, when your shear requirement is higher and higher, your moment capacity is almost reduced and reduced. So you can design, you can place the web plate like that ki your beam shall be optimized. In the case of higher shear, you can increase the thickness of the web and reduce the thickness of the flange. This fourth stage is the composite beam. This is the positive moment resistance. The positive moment resistance is also given in your codal value. When we are designing, the neutral axis is placed coming into three stages. One case, your neutral axis is placed in the slab. This is when you are designing the positive moment resistance, almost 95% of the cases, your neutral axis coming to a slab only, not a flange or the web. The second is your neutral axis coming in the flange. Third is the neutral axis coming into a web. Fifth, you can check this plastic shear capacity as per code. When the web is slender, means your value of slender is 67. The classification of the web is more than 67 epsilon. The shear capacity is reduced by this formula. Sixth, when composite beam is when we are designing the beam with the shear connector. In the shear connector is registers the interface shear. Interface shear. When the interface shear coming to a picture to transfer the lateral load like an earthquake or the wind, then this transfer reinforcement coming to a picture. So we can design also this transfer shear as per the codal value. In right side, it is given the formula in the IS 11384 for the bottom reinforcement in the slab. Generally, it is for not for deck. It is for the pure solid slab only. When you are designing transfer shear, then the formula is giving in the Eurocode 4. This is the contribution of the deck sheet, concrete, as well as your reinforcement also. So we can check if the deck sheet is not sufficient for taking the lateral load, then you can provide the this again shear goes to the concrete, and it is not, then you can provide the shear reinforcement. Sorry. This is for considering the when you are designing composite beam, automatically this shear connector coming to a picture. There is number of shear connector in given in the boom. Was the headed shear connector. Second is channel shear connector. Third is some good connector provided by this Hilti also. Some type of bars also. It gives a different capacity as per the design. We are talking about only the headed shear connector. This is a very easy to erect at the site because the shear connector is in the numbers. When you are designing the 1 lakh square foot of the building, 1 lakh square foot of the building, 10,000, there is a 30,000, 40,000 shear connector at the coming to a picture. And this is the welded through the deck, and it's give the better stability. This is the connected to the deck and better stability against the transfer shear as well. The formula as given in the code. The first we are checking the shear capacity of the connector with the concrete area, and the second is the steel area. And third, the reduction factor for the strength for when you are providing the deck sheet the parallel to the beam and the perpendicular to the beam. This also given in the picture. There is 2-3 things more interesting in given. The distance between transfer distance between the shear connector should be more than 4 times of the diameter of the, and edge distance. This is a clear edge distance is the 20 mm in the given in ES or IS, but 25 is given in the 113893. The headed is 1.35, and this shear stud height is depending. This is the more the ribs. This is the 50 mm more than the ribs. At least height of the shear connector, whatever the rib side plus 50 mm. This is given in the all the international as well as Indian code. The thickness of the flange, when we are welding to the flange, the thickness of the flange should be not less than d by 2.5. The longitudinal direction, as per international, the spacing between the connector is more than 5D, but it is the different formula given in our Indian code. Again, the partial shear connections is also coming to a picture. When first, this is the thing, when you are designing the T-beam, there is some compressive force and the tension force. Whatever the minimum force is there, this is behavior interface shear to the beam. Okay, is total 100% interface shear. And sometimes we are not able to provide numbers of shear connectors in the total length of the beam, so that we are reducing. Suppose we require the 100 numbers of the shear connector, and we are only able to provide as per the ribs, as per the spacing. This is a 80 mm or 80 or 60. Then we again calculate the capacity, positive moment capacity of the beam, depending upon the 60 numbers of shear connectors, 60 numbers of the shear connector. This is called partially shear connection. As per the Euro code and the American code, the minimum partial shear connection is the 25%, but Indian code, it gives you a NP, MR. This is the maximum. But the minimum value not given in our IS 113384. But internationally, we can go with the 0.25%. Again, this shear connector capacity is reduced by the fatigue strength. But generally, it didn't come into a buildings. It comes into a bridges where the cyclic loading is very, very higher. The shear capacity of this shear strut is reducing depending upon the number of cycles. Serviceability check. This is a deflection. You can increase this. This presentation is available in your session. You can take the total presentation. This is not required to take the photo. Okay. The serviceability is depth. We can combined E. We can calculate the combined E based on your T beam, like effective concrete as well as the steel. So this is the formula I, gross I. The deflection is based on the gross I. Okay, but this is the gross I is coming to a picture after the solid, after the setting of the concrete, not a previously. So deflection also we can check at the compression. This is the construction stage as well as the composite stage. First, the composite construction stage deflection. So we will provide the camber, whatever the deflection is coming under the construction stage, so that we can reduce the deflection in the beam. After 4 crore of square feet of the building, I am providing total deflection, and it is 100%. My experience is 100% nullify the deflection by the pre-camber at the construction stage. Last serviceability, second serviceability, the vibration. Vibration is coming. We can check the vibration. Some good document given the SCI 354. There is a given in the formula for the vibration. Is very extensive. This is based on the research, but our Indian code doesn't give any good formula. So you can use SCI 354 publication for the vibration check. There is 3 or 4 types of the vibration check. First is 18 by root delta. This is your vibration is directly in proportion to the deflection of the system, like slab plus primary beam plus secondary beam. This 7.1 given table of SCI 354. It gives the stiffness. Whatever the stiffness gives, this is stiffness gives the for slab, for secondary beam and the primary beam. They are the vibration check for the whole system, not for the single beam. And third one is gives as per the ICI, AISC. It gives the they will check the acceleration, AW. It's if you are designing with the E-tab, the direct formula coming to a picture. The more accurate method determining the yielding of the deflection. I have already told you that at the hogging moment area, the steel concrete is cracking. So due to cracking of the concrete, there is some movement redistribution in the happens in the system. So your deflection slightly increase by the cracking of the moment. when the hogging, in the hogging moment area, cracks are there. In the sagging moment, there is no crack. So there is some definition given in the every code, the cracked concrete or uncracked concrete. This is for the hogging or sagging area, not other than else. This is the analysis of the beam. This is the divided into two parts, elastic analysis and the plastic analysis. Elastic analysis is the based on direct triangular stress diagram, and this plastic is the rectangular diagram. And the elastic is for the semi-compact classification. And the plastic, you can go the use class 1, class 2, or your plastic or compact section only. Because in the both section, the rotation is allowed. That's why this rectangular stress curves is developed. Otherwise, it is not developed. And this is my good topic, the redistribution of the forces. In the redistribution of the forces, when you are designing the plastic analysis design based on the plastic theory. Develop the plastic hinge in the beam. When the one fixed beam is there, so when your load is applied, the one plastic hinge develop, and then further load is increased, the second plastic hinge develop, and the further load is increased, then the third plastic hinge will develop. It is the collapse mechanism, and due to that you can use the redistribution of the forces. As per this theory, you can apply the 100% of the moment redistribution, because up to this is the when you are up to the plastic hinge, there is no collapse coming to a picture. After the plastic hinge, there is some elongation come into a beam, and the section will goes under the plastic region. After the some time, it will collapse. Okay. So as per the plastic analysis, you can design, you can redistribute the force 100%, not. But practically it is not possible. You can redistribute 100%. It means your simple design. This is a simple design. So that's why the one code, this is a LRFO, they are giving some relationship, how the maximum redistribution you can do in the plastic section. This is the M, depending upon M and R, this R formula and the M formula, it given in the book. There is the books is LRFO by some University of the Italy. In this book published in the 1998. I think all theory is based on that book only. Now we come to the composite deck sheet. The composite deck sheet, there is a lot of things, because we found some of the, when you are going with the deck, everybody is using any deck. This is not practically possible. There is a number of pre-requirement for the deck you can use. First is, any deck you are using in the buildings or anywhere else, it gives you a fire rating with the concrete of slab. And you require at least UL or BS 476 certification by the vendor, then you can use the deck sheet. Otherwise, you cannot use the deck sheet for the fire rating. Then, if this is not available, if the certificate is not available, so you can use the deck sheet as a only sacrificial shuttering and design the slab like a roof slab. Okay, you cannot take the advantage of the deck sheet up to till unless you cannot take the certificate from the vendor. The minimum reinforcement, you get 0.25% of the unshored construction. And for shore construction, it is a 0.4. Generally, in the given market practice, they have designed the unshored construction, provide the 0.25%, and they are propping. Then when they are removing the prop, the cracks will develop at the beam location. So you can assure that this 0.4% shield should be there when you are providing shore construction. And the ribs is generally 40 to 80 mm higher, and 180 to 330 is available for the slim floors. The spacing, we are generally 3 to 4 meter, and 95 to 124 use more than 5.5 up to 5.5 meter. The deck sheet available 0.9 to 1.5 mm thick is the 275 GSM galvanized is required for the 50-year life. I am designing the one building, and client is, due to the cost, they have used the 120 GSM galvanized sheet. So I have repaired total deck sheet because of 275 GSM. Minimum thickness over the drift shall be a minimum 50 mm. Chloride admixture didn't use in the concrete because it will deteriorate your coating. Bending stress is the 0.6 time of your structure steel used in the deck sheet, or 260, whatever the minimum. Construction load, when you are designing this beam or column, composite column and composite beam, the minimum construction load is required. It is 1 kilonewton given in the AISC and the 1.5 given in the Euro or IS 1385. Deflection limit is 180 in the American code, and the Euro code is a 250, L by 250. Minimum bearing for the deck sheet. When you are putting the deck sheet on the I-beam, the minimum bearing is required 50 mm. But 2-3 location I have found it is not sufficient. That's why I will provide always the 75 mm. To just create, because the minimum is a 40-50 is given in the code, but it is not actual. When you are only single span sheet, it will fail. It will come out of the beam. The tolerance of the length tolerance is given in plus minus 3 mm. Fire resistance as per the local laws. So I am already told that the concrete, your concrete over the 150 mm concrete over the deck sheet gives you a 2-hour fire rating. If you require more than 2-hour fire rating, you put bottom steel and design with the fire engineering gives you a 3-hour or 4-hour fire rating. But deck sheet should be certified with the UL or BS 75. Openings in the deck sheet. Opening in the deck sheet is provided. A minimum is 300, maximum large is 300 to 7, large is more than 700. The minimum grade of the concrete as per the Indian code 25 or 20 mm, and the ACI, this is some written. This is 25 for the IS or Euro and 20 for the AISC. Temporary support you can provide when your span is higher. Suppose our sheet is designed for the 3.6, 3.7 meter. When the span is coming to a 4.5 or 5 meters, so you can provide the temporary supports for the designing of the deck sheet, and this is used as a sacrificial deck sheet, not a permanent deck sheet. The movement resistance given in the 3 different type. One is the neutral axis coming to above the deck, one is the ribs, one is the hogging. Now we are discussing about the compression column. These 2 formula, capacity of the plastic, axial capacity given in the code, one for this encased column, and second and third for the scale column. First is for the CFT, concrete infills. You can calculate the second is a styling flexural stiffness. Based on this is a non-damage surrender ratio. You can check. The formula is given in your IS 11384. Check for the effective long-term loading. When the PCR value is more than 10, so you can check the second effective long-term loading is considered or not. This neutral axis formula given in both the minor axis and the over minor and the major axis both side, and this formula used, you can calculate the neutral axis, and based on neutral axis you will calculate the plastic moment capacity of the column. Shear resistance, it gives you shear resistance gives based on the concrete reinforcement and the steel, and all together gives you capacity of the. Thank you.